Hello students. So in the previous class we started with examples actually based on level surfaces and how do we calculate the normal on a given surface, and also we introduced the concepts of directional derivative. So today we will practice few examples based on directional derivative, and afterwards if time permits then we move to our next topic. So to start with, let me start with one example on directional derivative. So today our example 1. So the example goes like this: find the directional derivative. So find the directional derivative of the scalar function f x y z. So we have a function in 3-dimension geometry. This function is x square y z plus 4 x z square at the point. So as we know, we always have to calculate the directional derivative at a certain point, and at the same time we also need to have a unit vector towards in the direction of which we will calculate the directional derivative. So at the point, what is the point here? The point is 1 minus 2 minus 1 in the direction. So this is our direction of the vector 2i minus j minus 2k. All right, I, j, k are the unit vectors. So let me adjust my chair first. All right. So here, so now we are going to solve this. So here the given scalar function, the given function is f x y z equals to x square y z plus 4 x z square, and in the previous class we saw the directional derivative of a given scalar function at a point p is given as a gradient of that function at the point p times the unit vector in the direction of which we are calculating the directional derivative. So here first of all we need to calculate the gradient of this function at the point p. So this is our point p. So we will calculate gradient of f, which is a vector quantity, and gradient of f would be del x of f, del y of f, and del z of f, and then k. So if I do partial derivative with respect to x, then this will be 2 x y z plus 4 z square times I, and then del y. So this will be x square z. The second term does not contain any y, so the derivative of second term with respect to y would be 0. So here it will be j, and del z of f. So this will be x square y plus 8 x z times k. All right. So that's our gradient of f, but we need to calculate the gradient of the function at the point p, because that's where we are calculating the directional derivative. So what is the value of gradient of f at the point p? So this is one of the notations to write gradient of f at the point p, and the point p is 1 minus 2 minus 1. So the value is, we substitute all these things, so 2 times 1 times minus 2. So this is very simple to do, and I am pretty sure you can be able to do this simple calculation. I plus you substitute the value for the rest of the variables here in I and j, in j and k. So ultimately if you calculate, then at the end you will be able to obtain 8i minus j minus 10k. So that's the gradient of the function f at the point p. and it is being calculated for substituting x equals to 1, y is equals to minus 2 and z equals to minus 1 in this expression here. All right. So, that is our gradient of f. Now, in order to calculate the directional derivative, we need the unit vector. So, here in this case we have the given vector, but is it a unit vector? It is obviously not, because if it is a unit vector, then the modulus of this vector should be 1. So, that is what we mean by unit vector, that the mod of that vector is equals to 1, but in this case it is certainly not. So, for this vector we will obtain a unit vector, and we will see how we do that. So, the vector in the direction of which the directional derivative dd is supposed to be calculated is given by, so what is the vector? We have 2I minus j minus 2k. So, I call it as, let us say, A. So, this is my unit vector, this is my normal, how to say, a normal vector. So, well, not that normal. So, this is basically the given vector, do not focus on normal or anything else. So, this is the given vector. From here I have to obtain a unit vector. So, the unit vector will be obtained by dividing the vector A with its magnitude, right. So, the given vector is 2I minus j minus 2k, and when we divide it by its magnitude, it will be 2 square plus 1 square plus 2 square. So, it will be 9. So, we take 1 by 3 out, and then it is 2I minus j minus 2k. Now, it is a unit vector. So, if we take the how to say magnitude of this a cap, then this will yield 1. So, that means this is a unit vector. Therefore, the required directional derivative of f at p, what is our p? P is 1 minus 2 minus 1 in the direction of a cap, is given by directional derivative df at a cap is equals to gradient of f dot a cap. Here, instead of a cap, I will write a, because we are calculating basically in the direction of a. So, it does not matter whether we write a cap or a, it is just that if we write a here, in the formula we should be careful that we always write the unit vector, because here we have a unit vector always in the formula. So, the directional derivative, I have chosen a notation df, although the notation does not play a big role here. You can ignore the notation and use your own notation for the directional derivative. This is not universal in a way, this is just my notation to signify that directional derivative of the function f in the direction of a cap. All right. So, now here we have gradient of f at the point p dot a cap. Now, gradient of f at the point p is given by 8I minus j minus 10k. So, 8I minus j minus 10k dot a cap. A cap is 1 by 3 2I minus j minus 2k. Now, we calculate this dot product, and this will be 16 plus 1 plus 20, isn't it? Yes. So, we will ultimately obtain 37 by 3. So, directional derivative of the function f at the point p in the direction of this vector a is given as 37 by 3. So, of course, it is a scalar quantity, and it is calculated in this fashion. All right. So, this was our first example. We will practice few, like 2 or 3 more examples just to make the concept clear. let us consider an example. Find the directional derivative of a scalar point function f in the direction of coordinate axes. So, this is our example 2. So, it is also a very interesting example. We have to calculate the directional derivative of a function f in the direction of coordinate axes. So, that means if I draw my coordinate axes, so this is x axis, this is my y axis and this is z axis, right. So, we have to calculate directional derivative in the direction of coordinate axes, that means in the direction of x axis, in the direction of y axis and in the direction of z axis. So, when we are calculating in the direction of x axis the directional derivative, so then in that case what will be our unit vector? So, if we are calculating the directional derivative in the direction of x axis, that means the unit vector is basically the vector along this direction is actually I cap, because x axis is perpendicular to yz plane and the unit vector for this x axis in a way is actually I cap. So, I cap is the unit vector in the direction of x axis and our a cap previously in the formula is actually I cap. So, I is the unit vector which is perpendicular to yz plane and it is along the direction of x axis and therefore, we use it as a normal in this case. All right. So, let us see what is our directional derivative in the direction of x axis first. So, we have to calculate along the coordinate axes, that means we have to calculate the directional derivative along the x axis, along the y axis and along the z axis. So, we have to calculate the directional derivative along all these 3 axes. All right. So, let us see for the given, let me write for the given scalar function or scalar point function f x y z, gradient of f at any point x y z is the vector del f del x, del f del y and del f del z. All right. So, that is our gradient of f and at any point p. So, that point p is x y z. So, I can write it as p and then I can write p at here. So, this is the gradient of the function f at any point p x y z and therefore, the directional derivative or the directional derivative along x axis is, so I will write df at the point p is equals to gradient of f at the point p dot a cap, and a cap is the unit vector along x axis. So, along x axis the unit vector is given as I cap. All right. So, we will write gradient of f at p dot I cap. Now, if we take the dot product of del f del x I plus del f del y j plus del f del z k, with I, then in that case only first term will survive, the rest of the term will be 0, because the component of j and k is 0 in case of this vector. So, here in case of this vector, j and k components are 0. So, when we take the dot product, only del f del x will survive, right. So, del f del x times I plus del f del y times j and del f del z times k dot product with I. So, if I take the dot product, then this will yield del f del x. So, that is the directional derivative of the function f at any point p in the direction of x axis, right. Similarly, the directional derivative of the function f at the point p along y axis will proceed in the similar fashion, and this will be basically del f del y, and similarly the directional derivative along z axis for the function f at the point p is del f del z. So, df at p is del f del z. So, basically in this case we got 3 directional derivative, and each one of them are directed along 3 different along 3 different directions. So, the first one is directional derivative along x axis, the second one is directional derivative along y axis, and third one is directional derivative along z axis. And you just have to know that I, j and k are the 3 unit vectors along x, y and z axes respectively, and rest of the things are very easy. So, this is another interesting example. So, you might be given a function f as x square y plus 3 y square z, and then you will be asked to calculate the directional derivative along x axis. So, you just have to calculate these gradients, and based on that you just take the dot product, and if you are asked to calculate just along the x axis, then you just calculate del f del x, and that will be your required answer at a point p. So, this is an interesting example which I wanted to show. We will move on to our next example, example 3. So, find the directional derivative of the function f x y z equals to x square minus y square plus 2 z square at the point p 1 2 3 in the direction of the line PQ, where Q is the point 5, 0 and 4. All right. So, here we are asked to calculate the directional derivative of the function f, which is given at the point P, but instead of giving a vector to in the direction of which we are supposed to calculate the directional derivative, we are given another point, and the vector which you obtain by joining P to Q, along which we have to calculate the directional derivative. Now, if you are familiar with vector algebra, if you have 2 points, let us say P and Q, then the vector P Q can be obtained by writing P Q as O Q minus O P. So, you take the distance from the origin, and then you take the for Q take the distance for P from the origin, and then you subtract them, and that will give you the required vector P Q or P to Q. So, that is exactly what we are going to do here. So, first of all, in order to calculate the directional derivative, we need to calculate the gradient of the given function. So, that is where we start from. So, here the given function is f x y z equals to x square minus y square plus 2 z square. Then del f del x I, del f del y j and del f del z k. So, when I take del f del x, then it will be 2 x I, then minus of 2 y j and then 4 z k. So, that is the required gradient of the function f at the point p. In general, the gradient of the function is given by this way. Now, we have to calculate the gradient of the function at the point p. So, the point p is 1, 2, 3. So, that means we have 2 times 1 times I minus 2 times 2 times j plus 4 times 3 k. So, this will be 2 I minus 4 j plus 12 k. All right. So, this is the required gradient of the function f at the point p. Now, we have to calculate the directional derivative along the direction of p to q. So, the vector or the direction vector is p to q, right. So, p to q can be given, that is let me write this in a clear manner. So, that is p to q is equals to O q minus O p. So, O q is, what is that point? 504. So, we have 5 I plus 0 z plus 4 k minus I minus 2 j minus 3 k. So, this will be 4 I minus of 2 j plus k, right. So, along this vector p to q, we have to calculate the directional derivative. I will call it as let us say a vector. So, say p q is our vector a, all right. So, from here I can write say. So, from here a cap is a by mod of a. So, this will be 4 I minus 2 j plus k divided by 16 plus 4 plus 1. So, this is basically 4 I minus 2 j plus k divided by square root of 21, all right. And now, the required directional derivative of f at the point p is given by gradient of f at the point p dot product with a cap. So, gradient of f at the point p is 2 I minus 4 j plus 12 k. So, this is 2 I minus 4 j plus 12 k dot product with 4 I minus 2 j plus k square root of 21. So, whatever you get after the simplification. So, here you just have to take the dot product and ultimately we will be able to obtain 28 by 21 times square root of 21. So, this is ultimately 4 by 3 square root of 21. So, that is the required directional derivative of the function f in the direction of p to q. So, here the direction vector, let us say, is not given and we had to calculate the direction vector by just writing p q as o q minus o p. You just substitute the value, take the difference, and that is your required direction vector, and from there we have to calculate the unit vector. So, we divided it by its magnitude and that gave us a cap, and therefore, the required directional derivative of f at the point p is the gradient of f at p dot product with a cap, and that is your required answer. All right. Now, we will calculate another example. So, what is So, we know that directional derivative is the rate of change of function f with respect to the distance in the direction of a unit vector. So, df ds. So, df ds is the directional derivative or the rate of change of the function f with respect to the distance or length in the direction of a vector a cap or a whatever we would like to say, basically a cap. So, from that formula, the directional derivative is nothing but gradient of f at a certain point p dot product with a cap, right. So, this directional derivative, it will be maximum in what direction? I mean, what is the maximum value of this directional derivative? In which direction would it be maximum? So, the thing is, the maximum value would be attained if we consider this a cap as a unit vector. So, it is actually a unit vector, but if let us say if that's equals to gradient of f by gradient of mod of gradient of f, that means its maximum along the direction of gradient basically. So, instead of considering a is equals to any arbitrary vector, if we consider a is equals to gradient of f. So, that is what I am trying to say, that if we consider a is equals to gradient of f, then in that case a cap is gradient of f by gradient norm of mod of gradient of f, and when we take the dot product, then it will be basically mod of gradient of f. So, that means the maximum value is attained when the directional derivative is equals to the gradient of f, mod of gradient of f. So, that is the maximum value. So, what I am trying to say is that if we have df equals to gradient of f a cap, and the a cap, if I write a cap. So, a cap is basically a unit vector along which we are calculating the directional derivative. So, a cap is equals to gradient of f, then in that case this will be mod of gradient of f, and this is the maximum value of the directional derivative. So, in the direction of gradient of f, the maximum value is attained. So, basically the maximum value of the directional derivative is attained in the direction of gradient of f. So, instead of taking any vector a, if you take gradient of f itself, right. So, you have a given surface, if you take a as the gradient of f, and here instead of any a, if as a cap, if we take gradient of f by mod of gradient of f, then we will basically be left with mod of gradient of f as the directional derivative, and that is the maximum value of the directional derivative or maximum rate of change of the function f given as a scalar function. So, this is a very vital result, that in the calculate the directional derivative in the maximum rate of in the direction of maximum rate of change. So, that direction is basically the direction of the gradient of f, and this is the message I am trying to convey. So, the direction of maximum rate of change is basically the gradient of f. So, along which the function is how to say has the greatest or attains the maximum rate of change, and that can be basically the directional derivative along the direction of maximum rate of change is given by mod of gradient of f. All right. So, we will do the same thing here. So, basically we will try to solve this example in our next class, and we will stop here for today, and we'll continue with the same example in our next class. We'll try to solve this, and then we will continue with some more examples on directional derivative. So I thank you for your attention for today, and I'll see you in the next class.